Hi folks, I'm going to go over the advanced math practice test for the quadratics unit. This is not going to be doing anything that isn't in the answer key already, but it's a chance to listen to somebody talk through the questions, which you might find useful. First page is asking you to basically solve a quadratic function. Find the zeros of a quadratic function. Same function, 4 different ways. So number one, find the zeros. And find the zeros means that we'd want to find the values of x that make the function 0. In other words, if you put the zeros into the function, it would evaluate to 0. To do this by factoring, we want to look at this function. Just rewriting the function in the question. And we want to think of it as a product of two factors. And the form of this is, in the simplest case, is going to be an x leading term in each factor, and then we'll have a number, plus or minus a number as a second term of each factor. And when we distribute these two factors together, we're going to see that the middle term of my quadratic is equal to the sum of these two numbers, and the constant term is going to be equal to the product of these two numbers. Now, this is a simplified way of looking at it that really only works well when the leading coefficient of the quadratic is 1. But again, first page is kind of the simpler questions. So that's what we're doing here. So numbers that would satisfy this condition would be -3 and +1. So we have one factor is x minus 3, the other factor is x plus 1. If we multiply those together, we would get x times x, or x squared. We'd have -3x and a +1x, which would add together to give me -2x. And we have -3 times +1, which multiply together to give me -3. And this is what f of x is equal to. Now, finding the zeros means we're basically saying what values of x are going to make this equation, the right-hand side, rather, evaluate to 0. So we're solving this equation. And when it's in factored form, this is actually kind of cool. This right-hand side will equal 0 when either of these factors, this one, the right one, or the left one, is equal to 0. So that's what we want to think. If either of them is 0, the whole expression on the right-hand side is going to be 0 because they're multiplied together. So this leads to two separate little equations that we could write. We could say x minus 3 equals 0, or we could say x plus 1 equals 0. We could solve those independently. In the first case, we'd get x equals 3. Now that is one of the zeros of the function. If you plug 3 or substitute 3 in for x, then the original function is going to evaluate to 0. And the other solution we're going to get by solving this right-hand equation is x equals -1. So if we substitute -1 for x in the original function, we're going to find that that function evaluates to 0. So those are the two zeros. Now moving forward, we want to use the exact same function and solve it by using the quadratic formula. So what we're being asked to do is demonstrate that we can, evaluate the quadratic formula with these coefficients. And coefficients here are in standard form are a, b, and c. In this case, the coefficient a is really 1, even though we didn't explicitly write it. Coefficient b is -2, and constant c is -3. So we're going to substitute these in for a, b, and c in the quadratic formula. And whatever that evaluates to are the values of x that make this function equal to 0. So when you're using the quadratic formula, you're basically setting up an equation that looks like this. 0 equals x squared minus 2x minus 3. So in this situation where we have the quadratic equal to 0, we can substitute the a, b, and c coefficients into the quadratic formula and find the values of x that make the equation work. So let's do that. And what we're doing at that point is we're actually solving for x. So x will equal -b plus or minus a square root of b squared minus 4ac all over 2a. So let's insert this. So -b means negative minus 2 because the b coefficient is -2. So we're going to say negative minus 2, and then plus or minus the square root of a bunch of stuff, b squared, so that's going to be negative 2. I'm putting this in parentheses to emphasize the fact that we are squaring negative 2. It's not negative 2 squared, it's negative 2 squared minus 4 times a, which is 1, c, which is negative 3, and this is all over 2a, or 2 times 1. So we need to evaluate this. So negative times a negative is a positive, so we have 2 plus or minus the square root of, now negative 2 squared is going to be a positive 4. Negative 4 times 1 times negative 3 is positive 12, and 2 times 1 is 2. So, continuing, 2 plus or minus the square root of 16 over 2 is 2 plus or minus 4 over 2. Now, we have in the numerator and denominator a common factor of 2, which we can cancel out. So we can do this because this has got 2 as a factor, and this has got 2 as a factor, so we can cancel them together with this denominator, which has 2 as a factor. So we end up with 1 plus or minus 2 all over 1, or just 1 plus or minus 2. So 1 plus 2 is 3. That's one solution. And 1 minus 2 is negative 1. So x equals negative 1 is the second solution. And we're happy with that because it matches the answer that we got for number 1. Now, number 3 says, let's see if we can do this by completing the square. And what we're doing by completing the square is essentially we're rewriting this standard form quadratic in vertex form. And again, we're solving for the case where 0 equals. And there we go. Let's look at all those funny lines. I used to complain that my pen would do this when I was working on a Mac, but it's doing to me on a Windows computer as well. So what we want to do is we want to imagine that this part of the original quadratic is a result of squaring an x plus a number. So the leading term here is x. And you remember up here when I said that the sum of this number and this number would equal this number. Similar idea here. We want a value here which when doubled or added to itself will equal negative 2. So that would be negative 1. So this would all be squared, and if we square that, we're going to get x squared minus 2x. Ooh, we're going to get more than that, actually. So this isn't quite right. So I'm temporarily thinking I'm going to have a negative 3 over here, but I really want to figure out what x minus 1 squared really is. So it's not quite equal to this yet. So x minus 1 squared would be x squared minus 2x plus 1. So the first part of this very nicely matches what I started with, the first two terms of the standard form quadratic. But by writing this as x minus 1 squared, I got this extra plus 1. And I don't really want that because it's changing the value of my expression. So I'm going to subtract it out. And then I'm bringing in this minus 3. So the whole point of doing this a plus 1 and the minus 1, the plus 1 is here because x minus 1 squared is x squared minus 2x plus 1. The minus 1 I inserted because I don't want to change the value of my quadratic. I don't want to change how it evaluates. I don't want to change its meaning. So I'm basically canceling this out. And then minus 3 is here because, well, the minus 3 was there in the first place. Now that I've done this, I can take this piece, which is a standard form quadratic, and I can truly write it as x minus 1 squared because that's what it is. The minus 1 and the minus 3 become minus 4. And this is equal to 0. So I've now basically rewritten the standard form quadratic in vertex form. And vertex form is easy to solve, relatively easy to solve. So basically, I want to get x by itself. So I'm going to start peeling away the pieces around the x. So 4 equals x minus 1 squared. And now I need to take the square root of both sides. And when I do that, I'm going to get a plus or minus. So the square root, do this. Square root of 4 is 2. So this becomes plus or minus 2 equals x minus 1. I'm going to add 1 to both sides. I get x equals 1 plus or minus 2. And I think we'll see up above, that's exactly what I ended up with after using the quadratic formula. So I'm getting basically the same answers, just exactly what I hope to see. So x equals 3 is one solution, and x equals negative 1, or 1 minus 2, is the second solution. Easy peasy. Again, the important thing was like showing that you can make your way through that process and arrive at the same answer. And if you end up with a different answer than what you expect, then you know that something's gone awry in your process. Lastly, we want to think about finding the zeros of function by graphing the function. And there are a number of ways of approaching that. We could try graphing this vertex form equation, but I want to show you something a little bit different. I want to use a little very tiny formula for finding the vertex x coordinate, also known as the, here we go, undo that little scribble, the x coordinate of the vertex, or the axis of symmetry, is equal to negative b over 2a. And if you're curious about that, it's actually the same thing as sort of the beginning of the quadratic formula, is negative b over 2a. That's giving you the axis of symmetry of the parabola. And I can look at my standard form quadratic, and I know negative b is going to be 2. Well, negative 2, b is negative 2, all over 2a. A is 1, so this becomes 2. And so this is, in fact, the x coordinate of the vertex is 1. So we know something about the vertex location. We can easily find the y coordinate of the vertex by substituting x equals 1 in the original equation. So f of 1 is equal to 1 squared minus 2 times 1 minus 3, which is 1 minus 2 minus 3 is minus 4, negative 4. So f of 1 equals negative 4. That means our vertex is at 1, negative 4. So I can go to my graph, and down here at 1, negative 4 is my vertex. So how does this help me solve the quadratic? Well, knowing where the vertex is key. Second thing is, what's the leading coefficient is 1. Remember, all quadratics are simply a transformation of a parent function. A parent function is y equals x squared. And the x squared function is very straightforward. You go to the right one, you go up 1, 1 squared. you go to the right 2 from the vertex, you're going to go up 4, 2 squared. If you go to the right or left 3 from the vertex, you're going to go up 9, which is 3 squared. So the shape of this thing is well known with respect to the vertex. If the leading coefficient is positive, then it's concave up. If the leading coefficient is negative, it's concave down. Well, this is a positive leading coefficient of 1. The vertical stretch is 1, so it's going to behave, it's going to shape, it's going to look exactly like the shape of that parent function y equals x squared. So, easy to draw on some other points. If I go to the vertex and go over 1 and up 1, I got a point right there. Same thing to the left, over 1, up 1 is another point. If I went from the vertex over 2, I'd go up 4. If I went to the left from the vertex 2 units, I'd be going up 4. And so graphically, visually, by looking at the graph, thinking about the shape of the parent function, I am arriving at some points for this quadratic that actually happen to land on the x-axis. So this literally gives me the location of the zeros. I can look at the graph and say x equals -1 or x equals +3. Those are my zeros. Those are the values of x that make the function 0. And I can truly sketch. Watch how well I do this. I can sketch the parabola as it passes through those points. Nice and smooth at the bottom, the vertex. I have my solutions. All right. So 4 different techniques. Alternatively, as I said, you could use the sort of the vertex form that you got in question 3, and that would tell you. That's one way of finding out where the vertex is to complete the square. Lots of different ways to do it. Part 2, we're looking at now we're looking more explicitly at a quadratic as a transformation. The function p of x is a transformation of f of x equals x squared, in which the vertex is shifted to 1, 2, and stretched vertically by a factor of -2. So write p of x as a function of x. Sounds scary. So the vertex, it's not really. So vertex is shifted to 1, 2. So the vertex has gone to the right by 1 unit. And I say that it's to the right 1 unit because the parent function f of x equals x squared has a vertex at the origin. So if the vertex has moved to 1, 2, it's been shifted to the right 1 unit and up 2 units. So it's to the right 1 and up 2. And we have a vertical stretch by a factor of -2. So as a transformation, let's say p of x. So we're defining p of x. So I start with p of x as a function of f of x. So we're going to write this transformation by modifying f of x. So I'm going to need to have f in here somewhere, parenthesis. Now, to get that shift to the right, we want to write this as x. Whoops, I keep doing that. I think there's a button on my pen that I keep pressing by accident. So I shift to the right by 1 unit means we'd say x minus 1 inside the parentheses, which means that when we put 1 in for x here, we'd have 1 minus 1, and we'll be evaluating the parent function at 0, and the output then would be 0. So in that particular case, we want to have actually 2 when x is equal to 1, so we need to add 2. So thinking about it as a function transformation, that minus 1 inside the parentheses gives us that shift to the right by 1 unit. The plus 2 outside the parentheses is giving us a vertical shift up by 2. And now finally, if we want to get this vertical stretch, we need to multiply the output of the function by -2. So we could throw a -2 in front of the f, which implies multiplication. We're going to multiply the output of the function by -2, and we're going to add 2 to that. So that gives us all of the pieces in the description in part 2. So that's writing p of x as a function of f of x. Now we want to write p of x as a function of x only, so we're going to get rid of the f, essentially. It's going to start the same way. We're going to say p of x is equal to, and it's almost the same thing, -2 times. Now, this piece here is saying f of x minus 1. And we have to go look again at the definition for f of x, parent function. It says whatever goes inside the parentheses after the f gets squared. Well, what went into the parentheses after the f in number 1 was x minus 1. So we want to take x minus 1 and square it. And then finally, this piece on the right, we just bring down as is. So these two answers for 1 and 2, they look almost exactly the same. The difference is that one of them says f of x minus 1, and the other one says x minus 1 squared. Two different ways of saying the same thing. One's using function notation, given that our parent function is f of x equals x squared, and the other one is explicitly stated as squaring the quantity x minus 1. To put p of x into standard form, we essentially need to multiply it all out. Again, we'll use p of x equals, and we'll explicitly say we're multiplying x minus 1 times x minus 1. That's what squaring means, and we're going to add 2 after all that's said and done. So -2 times, I'm going to put a big set of parentheses here. So x minus 1 times x minus 1, if we multiply the first terms, we're going to get x squared. The inner pair and the outer pair is going to be -x and -x. And then the last terms multiplied together will give us +1. So that's all the stuff that came out of squaring x minus 1. And then outside of that, we'll add 2. So we have -2 times x squared minus 2x plus 1 plus 2. Now we're going to distribute the -2 in here. -2x squared. -2 times -2 is plus 4x, and then -2 times 1 is -2. So that's distributing the -2 into the parentheses here. And then finally, we bring down this last plus 2, and we can write our final version, p of x equals -2x squared plus 4x. And the -2 and the +2 cancel out, and there's nothing left to do. So there is no constant term in our standard form. Doop. And okay, scribble, there we go. Standard form. Graph it. Okay, this is so nice. So up here in the description was everything we need to know to graph this. We know that the vertex is at 1, 2. So we can go to 1, 2 on the graph and say, there's our vertex. I even write it in, vertex. And everything else is stretches. There was no horizontal stretch described in question or part 2, but there was a vertical stretch by a factor of 2, and it was negative. So that means that our parabola, remember, we're transforming y equals x squared parabola, so it's going to be reflected over the x-axis. It's going to be concave down, and instead of being over 1 down 1, over 2 down 4, it's going to be going down twice as far. So I'll show you what I mean. So if we go over 1 to the right, because it's negative, we're going to go down not 1, which would be 1 squared, but we're going to go twice as far because the vertical stretch is -2. So we're going to go down 2 units. So there's another point. If we go 1 unit to the left, we're going to go down the same amount that we did on the right. We're going to go down 2 units, brings us to there. If we go over 2 units from the vertex, we should be going down in the parent function 4, but this is a factor of 2 stretched, so it's going to go down 2 plus 2 more, somewhere down here. And if we went 2 units to the left of the vertex, same thing, symmetrical on the left and the right. We have another point down there. So we can sketch the graph. It's god awful. It's the first time I've drawn on the tablets since, last year. What a mess. Anyway, so it's a concave down parabola. Not the same proportions as the parent function y equals x squared. It's got a vertical stretch of 2. So the parent function would be over 1 down 1. This is over 1 down 2. Parent function would be over 2 down 4. This is over 2 down 8. So hopefully, so for our assessment, I don't think you're going to be asked to graph anything because it's online, but you may be asked to identify graphs. I forget what it looks like. So again, I didn't have to do any math for that. I didn't have to plug in any values. I didn't have to evaluate any functions. I didn't need a calculator. I'm just making a parabola shape that's similar to the parent function parabola shape. It's just vertically stretched by a factor of 2 and upside down with a vertex at a certain place. So that's the kind of thinking we're looking for here. It's like, just cut it down to its simplest elements. Question 3, or part 3, getting a little more interesting. Find all solutions real or complex. Now, you can use a variety of techniques on these. What you should do is think about factoring first. If factoring is easy, then factor. If it's like already almost or in the vertex form, then solve it straight away. If it looks like a god-awful mess and you're not sure what to do with it, you could use the quadratic formula. So the first thing to do is write your equation so that it's a quadratic equal to 0. And the first one is not in that form, so I need to put it in that form by adding 4 to both sides. So we get x squared minus 14x plus 24 equals 0. And so for factoring, I want to think, are there two numbers that add together to give me negative 14 and multiply together to give me 24? And I think x minus 12 and x minus 2 would do the job. So there's an expression that's equivalent to that standard form. Multiply it together, it should work. And that leaves me with two equations that I can solve. X minus 12 equals 0, and x minus 2 equals 0. So x equals 12 or 2. And, with these questions also, if you have the time, I wouldn't jump to it right away, but if you have the time, you want to go back and check your answers on some of these things, you can take your solutions and literally substitute them in for x in the original equation, and it should work. If it doesn't work, then you either made a computation error checking it, or you made an error in the solution. So it can be a clue that you need to look at something. Number 2, is factorable? But let's say we wanted to use the quadratic formula instead. So negative b plus or minus the square root of b squared minus 4ac over 2a. So you could use that. Negative b would be minus 3 plus or minus the square root of b squared would be 9 minus 4. A is 2. C is negative 9. All over 2a, which is 2 times 2. Let's see, it'll be negative 3 plus or minus now 9. Minus times a minus is a plus, so we have 8 times 9 or 72. 72 plus 9 is 81. So you have the square root of 81. That's a nice number. Over 4 equals negative 3 plus or minus 9 over 4. So negative 3 plus 9 would be 6. So you have 6/4, or negative 3 minus 9 would be negative 12 over 4 would be negative 3. If we want to simplify that, of course, we would have 3/2 or negative 3. So that's what x is equal to using the quadratic formula. And you'll notice if you look at the answer key that's published for the practice tests, we factored it, got the same answer. So on number 3, here's a pro tip. If you've got something like this that's squared, and that's the only place the x appeared, you might just be able to go ahead and just use ordinary algebra to isolate the x. So I'm going to try doing that. I'm going to add 8 to both sides. 2 divide by 2 now. So x plus 4 equals 4. And then we'll take the square root of both sides. Remember to do plus or minus. So we have x plus 4 equals plus or minus 2. So x equals negative 4 plus 2. Negative 4 minus 2 equals negative 2 or negative 6. Now I keep thinking, I said find all solutions real or complex. We haven't found any complex solutions yet. So maybe number 4 has got a little trick up its sleeve. The form of this one at number 4 looks just like number 3, so I think we're going to use the same technique. I'm going to subtract 18 on both sides. So we have 2 x plus 3 squared equals negative 18. Oh, I see trouble ahead. I'm going to divide by 2 on both sides. So we have x plus 3 squared equals negative 9. Take the square root of both sides. We'll have x plus 3 equals the square root of negative 9, plus or minus. Okay, now square root of negative 9. Anytime you have the square root of a negative number, take the square root of negative 1 out of it, and we call that I, the symbol that represents the square root of negative 1. What's left behind is going to be the positive value, square root of the positive value. Now 9 is a perfect square, so that's nice. X plus 3 equals plus or minus I times square root of 9, which is 3. So plus or minus I3 or 3I. And now we'll solve for x, subtract 3 from both sides. So x equals negative 3 plus or minus. Now, it could say I3. You could say 3I. I think the convention is to put the I at the end. Except you wouldn't want to put it at the end if it ended up being to the right of a square root symbol, because then it would look like the I is under the square root. So be careful about how you write it so that it's very clear. If you're asked to come up with 2 distinct values, then you would say, well, negative 3 plus 3i would be 1, and then negative 3 minus 3i would be the other one. So that's 2 distinct values. They are complex. They have a real part and an imaginary part. All right. Now we're going to have some looks like some practice with working with the I symbol, the square root of negative 1. So we have an expression here, square root of negative 9, and an I. So we're going to see what we get. Now, In solving number 4 up here, we're solving an equation, solving for x, and we end up taking the square root of something. Along the way, we need to consider positive and negative values. If we're simply evaluating expression and we're trying to figure out what to do with the square root of -9, we don't need a plus or minus on that at all. We just get one answer because the square root function is a function. It only gives you one answer for a given input. So 3, now we're going to explicitly say is 1 minus 2i times 1 minus 2i, just to be clear. And the square root of -9, of course, is I times the square root of 9, which was 3. It's similar to what we did in the previous example. Now let's do this multiplication of 1 minus 2i to itself. So again, keeping the 3 here, and I'm going to put a big set of parentheses. 1 times 1 is 1. Negative 2i times 1 is negative 2i. 1 times negative 2i, doing the outer product, is negative 2i. And then negative 2i times negative 2i is positive 4i squared, close paren, plus 3i. I just changed the order of the I and the 3. Now, I squared is -1. That's the key thing. Anytime you see an I squared, say, hey, that's the square root of -1 squared should be -1. So this simplifies down to 3 times 1 minus 4i, combining the two I terms, minus 4, close paren, plus 3i. And now I can distribute the 3 in here. So 3 minus 12i minus 12 plus 3i. And now I can combine the I terms and the non-I, the real terms, and we should get -9 minus 12i. So that is a simplified version, simplified version of the original expression with any squared i's converted into their real version, their real format. So this is a complex number expressed in the a plus bi form. So we've written it with the real part first and the imaginary part second, just a convention. And then number 2, graph completely y equals f of x without creating a table of values. So that means we don't want to just laboriously plug different x values in and calculate it out and plot, tail number by number by number. So I want to think about this function as if it were a function transformation. And I see that it's in vertex form. So this is the negative of the x coordinate of the vertex, and that's the negative x, and this is the y coordinate of the vertex. So the vertex is at -1, -2. So let's go find that. There it is. There's my vertex. Let's draw an arrow to it just to say how excited we are. We know where the vertex is. So the second thing that's important is that vertical stretch. There it is. That leading coefficient is the vertical stretch. And so it's like drawing the graph for y equals x squared, the parent function, but we're going to compress it vertically by a factor of 1/2. So instead of going over 1 up 1, we go over 1 up 1/2. And same thing on the left-hand side, over 1 up 1/2. Instead of going over 2 up 4, we're going to go over 2 up 4 over 2, or up 1/2 of 4. So over 2 up 2. And the same thing on the left, we're going to go over 2 and not up 4. We're going to go half as far as that. We're going to go up 2 units. So we're building up a nice, beautiful quadratic or parabola that's been compressed to half its ordinary height. Instead of going over 3 up 9, we're going to go over 3 up 4.5, which is half of 9. And the exact same thing on the left-hand side. So there's a whole bunch of points. And it says graph accurately. So the whole idea with accurate graphing is figure out as clearly as you can where the points are, and then connect them with a beautiful smooth curve. Maybe even smoother than this one. Not very pretty. But, so there we have it though. There's a parabola, which is in every respect looks like a parent function y equals x squared parabola, except that it's been squashed to half its original height, and the vertex has been moved to -1, -2. And I didn't have to do any calculation, all except knowing what 1 squared is, and 2 squared is, and 3 squared is, and maybe dividing 9 by 2 and 4 by 2 and that sort of thing. Not a lot of heavy, you don't need a calculator for it, which is really, really slick. Part 5, the juicy stuff. Okay. So it doesn't even say what kind of function this is, but we could imagine that it's a parabola and it has roots. Now, roots is another word for zeros. These are the x-intercepts of the function g of x. We have no idea what the shape of the graph is, but we know that there's this point here at x equals 3, and there's another one at 4.5. It could be a parabola. it's a unit on parabolas, but it doesn't actually say. So then the question is, what are the roots of y equals g of x minus 2? So this is a transformation of g of x. What kind of a transformation? Well, we're subtracting 2 inside the parentheses. So that means every x coordinate, every feature of the original function slides 2 units to the right. I don't know what the shape is, but I know that this function will look just like the parent function g of x, but everything is moved 2 units to the right. So those roots that were at x equals 3 and x equals 4.5 are 2 units to the right, those x coordinates. So roots are at 3 plus 2 and 4.5 plus 2, or 5 and 6.5. Done. Again, no heavy math. It's just a transformation of the original function. So the features move around according to the transformation. That's all. Question 2, we have a ratio, a fraction of 2 complex numbers. And it would seem like if we divide one complex by a number by another complex number, we're liable to get as an answer another complex number, but we should be able to express every complex number in simple a plus bi format, which this is not. So we have to use a technique to do that. We basically want to get the imaginary pieces out of the denominator. And so the technique is to multiply this fraction by 1, but not just any one, a 1 in a particular form. And that form looks like the denominator of the original fraction, except where this original denominator was 2 plus 3i, our new one is 2 minus 3i. We're taking the imaginary part of this original denominator and making it the negative of what it was before. And because I'm multiplying by 1, my numerator needs to match my denominator. So this fraction, 2 minus 3i over 2 minus 3i, is 1. No imaginary part at all. It's 1. They're the same thing. Numerator and denominator, so they cancel out. It's 1. So we're not changing the value of this original expression, 1 minus 2i over 2 plus 3i, because we're multiplying by 1. Now the magic is when we try to multiply 2 plus 3i times 2 minus 3i, so just multiplying straight across the way you multiply fractions, you're going to get a 3i times 2 term and a negative 3i times 2 term, which will cancel each other out. So we really only need to look at multiplying the leading terms together and the trailing terms together. And when we do that, we're going to get 4 minus 9i squared. 3i times negative 3i is negative 9i squared. Now I squared is a nice thing. I squared is just negative 1, so we'll deal with that in a moment. But first, we also have to multiply the numerator by 2 minus 3i. And this one's not going to be as pretty. Won't have any canceling going on. So the leading terms, 1 times 2 is going to be 2. The inner product is negative 2i times 2, which is negative 4i. The outer product is 1 times negative 3i, which is negative 3i. And then, oops, make this longer. The last time the last is negative 2i times negative 3i is positive 6i squared. Okay, so now it seems to have made something that's even worse than it was before. We've got this long numerator, I've got I squared and all that stuff. But remember, I squared equals negative 1. So in the numerator, we have 2. We can combine these imaginary terms to get negative 7i. And then 6i squared. If I squared is negative 1, this becomes negative 6. 6 times negative 1, so negative 6. In my denominator, I've got 4 minus 9i squared. Now, I squared again is negative 1, so it's minus 9 times negative 1. So it's actually a positive 9, a minus a minus. So this becomes in the numerator negative 4 minus 7i. And then the denominator is 13. And really, we're really there. But if I truly want to write it in a plus bi form, I want to separate this fraction into 2 separate distinct things. So I would say that it is this real part, negative 4/13, and then this imaginary part, negative 7i over 13, or negative 7/13 I, either way. So this truly is a plus bi form. And by that, I mean that this real part is a, negative 4/13, and the imaginary side, the b is negative 7/13, and then the I is the I. So it's an a plus bi form. All right. Getting more interesting. Write an equation of a parabola with zeros of 2 plus or minus I. So the zeros we're imagining are 2 plus I and 2 minus I minus I. And if for example, if you think about a situation where you had real zeros, suppose the zeros were 2 and 3, suppose. Zeros are 2 and 3. Then you could say that the factors are x minus 2 and x minus 3. And that would be an equation or an expression for a quadratic with zeros of 2 and 3. So if y equals x minus 2 times x minus 3, that would have factors of 2, or it would have zeros of 2 and 3. So by similar reasoning, I could say here that we have factors of x minus 2 plus I and x minus 2 minus I. So that would be an expression. And if you actually could distribute the minuses in here, you get x minus 2 minus I, and then x minus 2 plus I. And if you multiply these together, you could use the box method. If you can keep track of all your products, you can just do it in your kind of in your head, and you would get y equals x squared minus 4x plus 5 as a result. I didn't, yeah. An alternative way of looking at this, it's kind of interesting, is to sort of think about how you might get zeros to 2 plus or minus I in the first place. So you might be thinking, if you were solving a quadratic in vertex form, you might be ending up at the very end with an equation that looks like this. -1 equals x minus 2 squared. So that if you tried to solve that, you would end up with plus or minus square root of -1 equals x minus 2, or x equals 2 plus or minus I. So that would be something you could do to arrive at 0, so 2 plus or minus I. Well, this expression would come from a vertex form quadratic that would look like this: y equals x minus 2 squared plus 1. And if you multiply x minus 2 times x minus 2 and add 1, you get x squared minus 4x plus 4 plus 1, which is the same thing as that. So two different ways of looking at that, sort of working backwards to the original vertex form quadratic, or writing out the factors of the quadratic based on the zeros, and then multiplying the factors together to get the standard form equation. All right, 2 more to go. Number 4, we want to write an equation of the parabola shown below. So we have we can think about it as a transformation. Let's suppose that f of x, a parent function, is x squared. We could write it as a transformation of that. We know that the vertex has been shifted to the right 4 units and up 8. So we could say that this is y equals f of x minus 4. It gives us the horizontal shift to the right of 4 units, plus 8. Now, this parabola is upside down. It's concave down. So we know we're going to have a vertical stretch that's negative. So the last thing to figure out is if there is actually a stretch as well. And I see that if I go from the vertex over 2 units, we're going down 8 units. Now, in the parent function, y equals x squared, or f of x equals x squared, if you go over 2 units, you'd go down 4. 2 squared is 4. Here, we're going over 2 units to the right, and we're going down 8. So instead of 4 for the parent function, we're going down 8. So this parabola is stretched vertically by a factor of 2. So we need to put a 2 in here. So finally, I'd say y equals -2 f of x minus 4 plus 8. So I'm thinking about this as a function transformation, but it didn't say to write this as a function transformation of anything. It says write an equation of the parabola shown below. So let me expand this f business into what it represents. It represents the square of whatever's in the parentheses. So I would say y equals -2 parenthesis x minus 4 squared, because that's what f does. It squares the thing in the parentheses, plus 8. And that's it. Yep. Scribble. All right. Last question. This is the only one where I think you might want to have a calculator, because it's asking you to square a bunch of things. Squaring 1.2, cubing 1.2, fourth power, fifth power, and so forth. So there are 2 components to this. One is the square, cube, and fourth and fifth and sixth power of 1.2, and the second part is to do the same thing with the I. So the first one is 1.2i. The second one, 1.2 squared, is 1.44, and then I squared. C, we take the 1.44, multiply it by 1.2, and I happen to have it written down here as 1.73, and then I cubed. 1.2 to the fourth is 2.07, then I to the fourth. For E, we have 2.49, I to the fifth, and then finally for F, we have 2.99, I to the sixth power. So then we have to say, well, what's I squared, I cubed, I fourth, I fifth, and so forth? Well, so we have to remember I squared equals -1, I cubed equals -1 times I, or negative I. I to the fourth is going to equal I squared squared, which is just 1. And then I to the fifth is going to be 1 times I, which is I. And then I to the sixth is going to be I to the fifth is I times I, which is -1. Okay, so this is actually, well, this is 1.2i. This is 1.44 times -1, because I squared is -1. This is 1.73 times I cubed was -I, is 2.07. I to the fourth is 1, so it's just 2.07. I to the fifth is I, so it's just 2.49 I, and then 2.99 times -1, because I to the sixth is -1. So now we can plot these on this weird plane. This is not an XY plane. This is a real and imaginary plane. What we're doing is called creating an Argan diagram. So you can actually plot complex numbers on a plane where the real axis is horizontal and the imaginary axis is vertical. So point A is at 1.2i. So you go to 1.2 on the imaginary scale. That's your point A. B is -1.44. That's totally real on the negative side of the real axis. So there's B. C is 1.73 times -I. So that's 1.73 right about there on the negative imaginary axis. So there's C. D is 2.07 on the real axis. That's right about there, positive 2.07. E is about 2.5 on the imaginary axis. So that's going to be about there. A, B, C, D, E. Whoops. And F finally is about -3. So there's F. And then we're going to connect them together in order: A, B, C, D, E, F. So it creates kind of an interesting spiral. It's always growing outward from the origin. And as you multiply by 1.2i, you also rotate counterclockwise by 90 degrees around the origin. So this idea of multiplying this value by I over and over and over again, you're getting results that are actually sort of rotating around the origin, which is a neat way of looking at it. So it's really freaky things that happen with complex numbers. That's a neat example. All right, we're done. So these last questions were kind of tricky. They're usually small point totals, and they get progressively easier as you go towards the beginning of the test, but also worth more and more points because those are the things that we think are most important of all. All right, so there we are, about an hour, and the full test has been completed. I kind of took my time. It really shouldn't take all that long, hopefully. Hope you enjoyed it, and good luck.